Greetings, welcome to Project Dig's 6th recap video. Project Dig is a 2D multiplayer automation survival sandbox game that I am developing entirely on Twitch and uploading all of the VODs to YouTube, along with recap videos such as this one. We're making a custom C++ game engine using these libraries over here, and this last week or so we've been working on hash maps, really quick hash maps, and then spent most of the time doing tile maps. So I'm going to recap that stuff, and that's it. So let's jump in. So hash maps are things like a STD map or unordered map, and it's how you can have a key and a value associated with each other. The standard library provides those, like the STD map and unordered map, but it's kind of like a very well-rounded map, and it can do kind of anything okay. But for us, we know what we're doing, and we want to try to take advantage of that. So I did some research on some possible hash maps and ended up going with, let me go to types here, the Google, or what they now call sparse hash maps. And so we're specifically using the dense hash maps instead of the sparse hash maps because that's what's best for us. So I made this using just a hash map, and that's how we can use the dense hash maps. So we kind of went through our entire engine and converted things over. I didn't actually do any stress tests to see what the performance difference was to like any degree really, but I believe it's faster. At some point maybe we will actually do that. I meant to, but I forgot. So one of the downsides to using this is we have to provide an empty key as well as a deleted or a delete key if we are deleting items in the hash map. So an empty key is just like, hey, if we ever, if something is ever empty, it goes into the empty key. Delete key if we ever want to erase something from that hash map. And we can see that being used in many places, such as our world. Here we have this entity groups. If we go to the header, you can see that that's a hash map of component bits entity list, and we need to set the empty key on that one. So an empty key has to be a key that we're never going to use, so we kind of need to make sure that that's like an invalid key. And same thing with the deleted key. And so sometimes that's a little tricky. You have to like reserve those, like, hey, this is invalid. So let's say like normally you might say 0 is invalid, or uint32 max is invalid. Now you have to say like uint32 max -1 is the deleted key, and uint32 max is the empty key, or something along those lines, and prevent the those two from ever being used as a hash key. But yeah, so that's what we did for that. Very simple, straightforward. The majority of our time was actually spent on the tile maps, so let's jump over to that. Here's an example of those keys needing to be used there. So tile maps. A tile map is, or what some people refer to as blocks. They're little blocks that are being rendered on the screen that's like representing the ground. Dirt, stone, clay, iron. We have a 2D side view game that we're making, like Terraria or Kriya. So we actually have multiple tile maps that we might be rendering. Like there's the main ground one, and then there could be the back wall that you could also place blocks onto, and maybe we'll even have other layers. I'm not sure about that yet. Haven't thought too much about the layering. So we want to be able to render that, set that up, have it in our world, be able to change it and render it efficiently and so on, or performantly. So what I ended up doing is I made this tile map, and to go along with the rest of the systems, we did this Tilemaps component, which is a world component. So instead of making a tile layer, for Korea I did a tile layer which belongs to a layer manager, and then I had a layer manager pointer that was attached to the world essentially. I said, let's get rid of that. We don't need all that complexity. Let's just make it so that we have this Tilemaps component that contains the maps, and we have a fixed number of them that's created, and that the tile map count is set off of the tile map enum that we can find here, which is right now just wall and ground, and we could add more to this, and whenever we compile it, it'll just add more. So it's pretty fancy. And then if we ever want to get access to our maps, we just say, hey, give me the tile maps component, just like what we've done with anything else. And so this is how systems are able to get access to the maps. If we look at this tile segment cleanup, we can see a good example where we tell the scheduler, hey, we are going to be wanting to use or write to the tile maps component because we are changing it. And then here we get the tile maps component, and we iterate over all the maps, and we clean it up, and we'll get over that in a bit. And yeah, so that's like the topmost thing, the tile map. There's a lot of stuff that goes into it, which is mostly all about the draw function, or rendering it to the screen, and we'll talk about that in a moment. So besides that, what I did is I made it so that we have this namespace tile that has a lot of helper functions to be able to get a tile from a map, or to set a tile, or check to see if a tile is empty or solid. I'm not 100% sure this is the best approach. There are some things I like about it, and some things that I'm I'm not sure. We could technically put a lot of these damage as well into the tile map, and maybe that would end up being the best solution. We'll see as we go on, see how we're wanting to access and use this stuff. Right now though, I was trying to keep the tile map itself just raw data. We don't really want there to be a lot of logic on this, and that's why I ended up putting it in here. It's I don't want there to be a bunch of logic on the tile map, because the tile map is part of the tile map component, and we want to keep the components simple data, just plain old data structures. So yeah, tile, and so one more thing I'll add to that is, so a tile map is composed of a bunch of tiles, which we can see here, and a tile, I'm trying to keep this as streamlined as possible, as small as possible. A tile only, the only real data it contains is information on how to render it, the quantity, because that can change whenever you're digging a tile. Let's say you're harvesting or mining some iron ore. We want to be able to decrement the quantity so we know whenever it actually does run out. And then we have a tile ID, and that's the ID to the actual data. So we have this tile data, which contains all of the unique information per tile type. So we have dirt or stone or iron, and each of those are going to have their own tile ID that will tell us things like which prefab it belongs to, or what's the durability or the priority, or if it's solid or not, or for auto tiles, or the frames for rendering it, and so on. So we can make a prefab. Right now it just looks like this, prefab.tile. We set it up. If we go over to our prefab, prefab.tile, we can see that all it does is it actually just says, hey, let's set up this tile component and add this tile or this prefab to tiles, and that actually will register it to our static like database of tiles, and that's actually just an array of tiles. Where's that tile ID? Where's the, oh, there it is. Yeah, so it's max tile data. Right now I say there's a maximum of 256 or 255 tiles, because I believe, yeah, it starts at 1, so invalid tile ID is 0. So yeah, adds it and then it returns it. So a tile component actually only contains the tile ID itself, which is awesome. So if we ever like have a dirt item and we want to look up like, you know, hey, is the item tile that we're holding solid, we can do that with this tile ID. Yeah, so moving on. One of the biggest challenges that we had with all of the Telemap stuff is really figuring out how to render it. I implemented a very simple solution where it's just like, hey, take this frame information, push it onto the list of vertex, or kind of it does this, is push it onto a list of like a vertex array essentially that we will then render later. And so it's kind of creating this big list and then renders it at the end of the frame, and it does that every single frame. We went from like 240 or whatever, 250 FPS, I don't remember exactly what it was, to 4. So we're like, okay, we obviously need to improve some things. 4 FPS is not quite going to cut it. So we went about trying to solve that, and that took a few days to figure out. I'll just kind of recap it because it's quite in depth. So what we ended up coming up with is using a static vertex buffer. So we split up the world. Let me show you a little graph I made. We split up the world into what I call segments. So a segment is 16 by 16 tiles, so you can think of it as like a grid. And then we index the segments, just like going across each row, 0, 1, 2, 3, 4, 5, go down to the next row, 6, 7, 8, 9, 10, 11, next row, and so on. And that's the IDs that we are assigning to the segments. And so each segment is going to contain its own rendering information. So that way, as you're moving around in the world, we're just rendering the segments that are visible on your viewport. And if you move far away from a segment, then we can say, hey, this segment is not being used anymore. Let's go ahead and clear that out. So that way we kind of like group up the data in big enough chunks that it's actually you know, saving some speed. We're not having to recalculate stuff all the time like as we were when we were doing it in individual tiles, but it's still in small enough chunks that we're gaining some performance boost, and we're not having to like recalculate, you know, the entire screen or half of the world every single time. And whenever a tile changes within a segment, we also have to recalculate it at that point. So yeah, there's definitely some considerations and the exact size of a segment. Unfortunately, we have that set up in sizes.h. We can always change the segment tile and the segment size. Yeah, this could change a little bit, but we can easily change these things here. So we don't have anything hard-coded. We never say like, oh yeah, a segment is 16 by 16 in the actual code. We just say, hey, it's segment tile size. And so we have our segments that then have a group of tile render groups, or sorry, a vector of tile render groups. And what that does is it contains the actual vertex buffer and the texture and the program and all of the information that we need to be able to render that group. And a group is any tiles that share the same texture and the same program, so that way they can be batched together. So the idea is that we'll have like dirt and stone and maybe some other tiles on one texture, and they'll almost always use the same program. And then we can batch those all together. So instead of having to do, 20 different calls, we can just do 1 or 3, whatever, however many tile render groups we're gonna have within that segment. And so one optimization we made was that whenever you change a block, we just calculate which tile render groups have actually changed based off of that tile and the neighboring tiles, and we invalidate those and we recalculate the data for those specific groups. And so the vertex buffer handle is being calculated whenever we need to, and I can jump over to that code. Down here is where we update the tile segment groups. So we actually update it here. We say, hey, let's figure out exactly what the frame is, what's the texture rect for this tile. Let's add it onto the down here we can see. Oh, here we call it add tile vertices. Oh, whoops, sorry. This is where we're actually calculating all the tile data, but we're not rendering it or adding it to the vertex buffer yet. So we're just calculating like, hey, which frame should this be so it auto tiles properly? Or does it have priority for the blending, etc. That's what we're doing up here. We're setting up the tile group, and then we end up calling the add tile vertices, and that actually adds the vertices to our vertex buffer. And that's where we're using like the frames and everything to figure that out. And so what this ends up looking like after all of that code is that we have this tile map, and you can see it's actually rendering properly. And if we hold down control, we can change the blocks. We can see auto tiles, and it's also blending with the neighbors, which is great. And yeah, we can change any of the blocks, and then also we can see, well, we're in release mode right now, so we have like 950 FPS or whatever. And debug mode, we were at 4, like I said. After all of these improvements, we got up to 300. So some huge wins there. So yeah, that's our tile map. If you're interested in hearing more about how that development went, I recommend checking out the actual VODs for it, particularly the last day where we kind of, I think actually it's the last 2 days, we made a ton of progress on it. So yeah, that's going to be the recap video. One thing I wanted to mention is that this is going to be the last Project Dig video I do for a little while, because I am going to be moving over to working on Korea, my previous game, for a while, working on an update for that. And once that's done, I'll jump back over to Project Dig and we'll pick things up where we're leaving them off. So yeah, that's it for now. I wanted to say thank you to my patrons on Patreon that are helping support me. I really appreciate it, guys. If you want to get access to the source code, you can do that through Patreon. So yeah, I want to thank Solvin and Big Gay Dave and Summit and Wacko for all of your support. I really appreciate it. And I will see you guys hopefully not too long. Thanks for watching.